Hello, so continuing on this weekly contest 340, the last problem, which is number of visited cells in a grid. So what this problem says is we get a matrix n by n grid, and we start off in the initial position of 0, 0, so top left corner, and you can do two types of moves. One is to the right and one is down, so there is no left or up. And the right movements that you can do and the down ones you can do for example from cell IK, so basically from cell IJ you can go to cell IK such that K is in the range between J plus 1, if we want inclusive, J plus 1 to J plus the value of that cell. Okay, so you can move in a range. It will be easier explained with a matrix in a second. And then you could also go downwards to Kj, where K is inclusive range I plus 1, and then the value of the cell plus I, and then the column stays the same. So what does that mean concretely? So it means, for example, here, this cell means you can go rightwards, you can go either to I plus 1 or all the way to I plus 3, right? But you can do that from I plus 1 to I plus 3, which means basically I plus 1, I plus 2, I plus 3. And then you could also do it the same for J. So here you can go from J equal to J plus 1 to J plus 2 to J plus 3. Of course, with the condition that you don't exceed the bounds. So what this means here is that you can go to column 1, and then you can go column 2, and then you could go to column 3. Okay? So this is because there is 3 here. And then down you can go 1. Basically, 1, you can add 1 all the way to the value of the cell. So you can add 2, and then you can add 3. Okay? And then from this to here, you can go plus 1 or plus 2 only. So you can go either here or here. But you can't go to this one. Okay? I hope that makes sense. And so the problem asks us the following: the minimum number of cells you need to visit to reach the bottom right cell from the top left one. So in this case, what we can do, an optimal solution here is to plus 1, plus 2, plus 3 is to do plus 3 all the way here. And then from here, you can do plus 1, because the range is plus 1 or plus 2, moving right by 1. And then from here, because 4, you can go plus 1, plus 2, plus 3, plus 4, and without exceeding the bounds. And so here, you can do plus 2, which is within the range to go here. And at this point, we have traversed cell 1, cell 2, cell 3, and cell 4. So 4 cells, so we return 4. And so you can notice here, one thing is that we did count the top left cell. The initial cell, we do count it. So that's the problem. Now, one thing if we look at the constraint here, a couple of things to notice. So first, the number of rows and number of columns can go up to 10 to the power of 5. Okay? So that already tells you that you can't do, and also m by n can go up to 10 to the power of 5. So this tells you that you can't do m by n squared, because then it would be 10 to the power of 10, and that would be too much. And it's saying also that the last element in the grid is 0. That doesn't matter too much, but yeah. And so let's see how we can attack this problem. Okay, so how do we tackle this problem? Well, the first thing to think about is, usually when we are given a problem where we want to find the shortest path, which is what we want to find here, because we want to minimize the number of cells we want to visit. So we want to go from the top left to the bottom right, and we want to minimize the number of cells we visit. So it's sort of a shortest path problem. And usually shortest path problems are solved with BFS, right? And this is shortest path on a graph. So you might think, okay, is this really a graph? Well, it is, because we know the nodes, right? It's the cells, And what are the neighbors? Well, the neighbors, we are given the relationships, right? It says from this one, the neighbors are all the cells to the right that you can add 1 to 3, right? You can add 1, 2, or 3. And for the columns, it's also all the cells where the column you can add 1, 2, 3. So for example, here for this one, what are the cells that you can add 1, 2, 3? Well, this one. Here you can add for j, so you can add for j from 1 to 3. So here and this one. What are the neighbors for this one? It's this one, and this one, because we can add 1, we can add 2, we can add 3. Now, what are the, let's take a different cell just to understand the neighbors here, a relationship. So for example, for let's say this cell, maybe let's take this one, this cell. What are the neighbors? Well, you could add 2 here, so these are the neighbors, and then you can add 2 here. Those are the only 2 cells. Now this cell here has no neighbors, right? You can't move once if you get there, you can't move. You can't reach the bottom right one. From this cell, you can't reach the bottom right because you can't move. The value is 0. Let's take another example. So this one, you can only move here, and then you will get stuck, so you can't reach the bottom right, or you can go here. Okay, so I hope now you understand. It's just the range given by the value of the cell. Okay, so we know that we can use BFS because this is real graph definition. It's just an implicit graph, and we can use the relationship that we are given in the problem. Okay, so normal BFS is easy to solve. We can just have a queue, and in the queue we can start off with 0, 0, which are the initial cells. And the first step, because we need to count the steps because or the number of cells we visit. We need to add them to the queue. Because we need to count the initial cell, we will start out with 1. And then we'll just do normal BFS, basically adding the neighbors, and each time when we reach the last cell, we'll stop and return the value of the steps, because BFS, since it visits the nodes level by level, the node, when we reach the bottom right, or when we reach the destination the first time, that's the shortest distance. That's literally what DFS does. Okay, so is this good enough? That's the question. Well, BFS is O of E plus V, so the number of edges and the number of vertices. Now, what are the number of vertices? Well, that's M by N, or the number of rows by the number of columns. So let's actually call it R by C. Now, the edges are the problem, right? Because each node has the value of the cell. The value of the cell can be up to R by C. So each node can have up to R by C, R plus C actually, sorry, because it's you add to on the column side, and you add to the row side. So R plus C for each node, and so it's R by C multiplied by this, plus this. So the dominant term is actually this one here. And so it can be up to R by C multiplied by R plus C. So you can see this is too big because the problem says this is up to 10 to the power of 5. This is up to the 10 to the power of 5. The entire thing is up to 10 to the power of 10. So it's too big. So we have to find an optimization here. Now, what is the optimization we can do? Let's think about it. Let's say, for example, when we visit this one, right? When we are first here, right? And so we add to the queue this one, and then we add this one, and then we add this one, because we want to add all the neighbors to the queue. Now, when we pop this one. Now, when we pop this one, we already added this one. Does it make sense to add it again? No, it doesn't make sense, right? And if we use BFS with the visited set, we'll probably skip it. But we skip it after we pop it from the queue. So we still incur the cost. And doesn't make sense to visit this one as well when we are traversing 4, because we will go 4 is the range from 1 to 4. And so should we add this 2 and should we add this one again? No, the answer is no, we shouldn't add it, because we already added it as part of this 3. And so how can we avoid re-adding, right? And similarly, that applies to the column. When we visit 3, we add this one, we add this one, and we add this one. So when we are processing 4, it doesn't make sense to add this 2 again and this 2 again, because they are already in our queue. And so that's the insight that we are looking for here. So how do we avoid it? Well, for that, let's actually see a little bit of a different. What if the value here wasn't 3 and was 1? Well, in that case, we'll visit just here, we'll visit just here. So in that case, it makes sense for 4, it makes sense to visit this. Let me pick a different color. For 4, it makes sense then to visit this. It makes sense to visit this because they are not visited yet. Okay? And then same thing here, it makes sense to visit these. So you can see here, the actual thing we want to do is we want to record the last place we reached so that we don't go to it again. So for example, let me actually give you another example to make this super clear. Let's say this here was 2. Let's say here we had 2. What should we do? Well, the first time we'll visit this, and then we'll visit this, we'll visit this. And so for 4 here, it doesn't make sense to visit this 2 because we already did add it to the queue from this. But it does make sense to go here because we haven't visited it yet and it's within the range for 4. Same thing for here. It doesn't make sense to visit this one because we already added it, but it does make sense to go to this one because we haven't done it yet. This one, if we add it, it would be redundant. Okay? And so what did we do? We only, for 4, we need to know what's the last place we reached so that we can start our queue, we can add to our queue just from that place. Okay, and this will be more useful as the matrix grow. So that's the idea. And so how do we do that? Well, to do that, we can just keep track of 2 things. What do we need? We need one for the rows and we need one for the columns. And so let's just have 2 arrays, right? So let's call them the furthest we reached because it's literally what they do. They save the furthest we reached. And so we'll have something called furthest in row, right? So this will tell us for each for each row, it will tell us what's the furthest one we reached. Okay, and then similarly we will have the furthest in column, let's call it. Okay, or we can even shorten it up with furthest row and furthest column. Okay, and so basically what this will help us do is for here, for example, when we reach 2, 0, 1, 2, right? When we traverse 2, we will record that for the first column here, right? Let's call it maybe furthest in row. Yeah, we'll just record the end row, so the last row we reached. So for example, here the last row we reached is 2. Okay, and then here the last row we reached, this would be 0, 1, 2. We'll record that we reached 2. Okay, so that next time when we are processing this 4, we don't need to start from just this one. Basically this one would be J. We don't need to start from J plus 1. We actually start from J plus the furthest we reached, right? And so we'll end up starting from here. I hope that makes sense, okay? And that's the optimization that we will do. And basically with this optimization, we'll make sure that we never visit a cell, we never enqueue a cell in our BFS queue multiple times, which will make our traversal be just the number of cells that we have, which will make it be just O of R by C, which is 10 to the power of 5, which would be within the limit. Okay, so that's the idea. Registers where we reached, the furthest we reached, so that we don't move past it. And then the rest is just normal BFS. And so let's implement this idea and make sure it passes. Okay, so let's start. So first we need just, I will just mark this as J to make it easier to use. And so the number of rows is just going to be the length, the number of rows there, and then the number of columns. And now we need our queue. That initial, we'll use just a DQ, normal BFS. And so we'll start out with the first cell. So tab left, 0, 0. And the first, we visit once, because we remember we start at this cell and we need to count it. So it's 1. And then we will do our BFS, which is just go into the queue and then queue.pop left. And that will give us the cell and then the distance or the number of cells so far. Maybe we should call it count. So just doing the template for BFS, which is if we reach the bottom right, so bottom right when both rows, we are at the last row and last column, then in this case we can just return the count so far, right? The count of the cells we visited, right? Because this would be the shortest number of cells we have, because BFS does the shortest path, right? And now we just need to keep track of the furthest we said in row, right? And then we need the furthest in column. And each of them is going to be just, this one is just going to be for each, because it's the furthest in row. Let's actually clarify this. The furthest in row, it needs to be, what's in row? In the row, you have columns, right? So this would be columns. And then for column, what's in column? It's the rows. And so this needs to be for each row. Okay. And so this is just will help us not traverse, not include cells, the same cell multiple times. Okay, so now after that, what do we need to do? Well, after that, we need to go through the neighbors for each cell. Okay, so the problem says here, right? So it's like this for the columns, and it's like this for the rows. Okay, so what's the start row and what's the end row that we need to traverse? Okay, so here the start, since this is I non-inclusive, this is I plus 1. And what is the end? Well, it's the last one like this. Okay, and so, but here we don't want to exceed the bounds of the list. So what if, for example, here we had 5? If we had here 5, then we should go here, we should go here, we should go here, but we shouldn't go past that. And so we should stop when we reach the number of columns. Right, when we reach the number of the number of rows actually. Here we should stop when we reach the number of columns, and down here we should stop when we reach the number of rows, right? And so that's why here we need to make sure we don't exceed the bounds. And so what are the bounds for the rows? It's just rows minus 1, because this is the last row we should access. Okay, we haven't yet used the furthest in row. We'll optimize with it in a second. Just bear with me. But now this is going to be our K for the row. Let's call it KR in the range of the start of the row all the way to end of the row, right? So like this. Now in Python, because Python, to actually get to this, we need to do +1. So that's what we do here. And now we just add it to our queue. Now what is this is the row, right? Because this is literally, we are traversing the rows. So we are going like this, because this is the rows, right? And so for that, we need to, the row is KR, but the J didn't change because we are going downwards, right? And so this would be J. Now, we just visited another cell, so our count needs to increase by 1, right? Okay, so now we don't need visited, because we will make sure in a second, we'll make sure that we use this farthest in row and furthest in column, which will prevent us from visiting the same cell multiple times. Okay, so now, but we'll use that in a second. Okay, so similarly for column, the start column again is going to be, since this is non-inclusive, from J plus 1. So j plus 1. And then what is the end column? It's just this. Okay. And similarly for the column, we need to make sure that we don't exceed the bounds. And so to do that, we'll just do min and the columns minus 1. Okay. And now for, let's call it KC because it's for the column. In the range of starting from column to end column, and in Python, again, we need to do +1 for it to work. And now we will append it to our queue. And so I didn't change, it's the column that changes here. And so KC, and then the count increased by 1 because we just visited this cell, okay? And then now we will do this. Now, if we finish traversing in our BFS and we didn't reach the top right, the bottom right, that means it's not reachable, so we return -1. Okay, so far just normal BFS. Now let's use this furthest in row. So what we are saying is that, what I said in the overview is that when we do this here, right, let's say if this was 2, so that this actually works. Okay, so if this was 2, we will do this for the first iteration, but for this 4, we don't want to go to this 2. We want to go from where we left off, so we want to go only to this one. And so that's where we need to go to where we left off. What is where we left off for the row? Well, where we left off is just furthest. Instead of I plus 1, we'll do furthest in row, right, for this j. Okay. So this will tell us in a row what is the, in a column here, what is the furthest row we reached. And so let's say if this was 2, the furthest row we reached would be, so this is 0, 1, 2, would be row 2. So that's what we'll get here for this column 0. So this tells us for this column, we reached row 2. And so we shouldn't start from row 1, we should start from row 2 here, from the row 3, because we already processed the row 2. And so that means we should start from +1. Because this is the furthest we reached, we already processed it, so we should start from the next one. That's the main idea here. Now, the thing is, what if the furthest we reached is actually smaller than I plus 1, right? What if it's smaller? Now, in what case can it be smaller? It can be smaller if we, so let's say this was 1, and the furthest we reached is here, or actually the furthest we reached is still 0, right? Then we wanna go here. We wanna go to I plus 1, and so that's what we are going to do here. Just max of this and I plus 1, so that we go to the furthest one if it's bigger. So that will solve our problem. Now this +1, we can just put it outside like this, and this should work fine. Okay, and this exact same logic by symmetry applies to the column. And so here it's going to be the max of the furthest in column, right, j plus 1. So this is furthest in column for I, because what happens is that when we are here, we want to know what's the furthest we reached in this row, right? So remember, it's in the row because each row and each column is handled separately, because when we reach here, maybe it's the furthest we reach it is here instead of here, right? So we want to do it for each row and for each column. I hope that makes sense. Now, what's the next step? Well, for each traversal, we want to fill these values for furthest in row and furthest in column. They are initialized to 0, and so how do we do that? So here, what does furthest in row for j become? Well, it's just going to be, because for this one, we traverse all the way to the end row, and this one will traverse all the way to the end column. And so this one is going to be just the max of what was before in that place. And the furthest we reached in the row, what's the furthest we reached in, what is the furthest we reached for this row? Well, it's end row. sorry, let me rephrase it. So what is the furthest we reached for column J? The furthest row we reached for column J here. Well, it's this one. It's the end row. That's the furthest we reached. And so it's going to be just exactly what we are going to use. And similarly for column, what's the furthest we reached in column for I? Well, it's just we did the loop. We did the loop all the way to end column, and so it's end column, but we of course take the max with the max so far in case from a previous iteration we had a max one bigger than it, right? And so that's the idea here, and this will be used for the second queue iteration so that each time if we went further we start from that point, right? And this will make sure that we don't visit any cell multiple times. Okay, so now let's run this, make sure it passes. So here is just we want to use J since that's how we defined it. And now let's run this. Looks good. Let's submit. Looks like we have one small problem. Yep, sorry, this should be in column. And let's submit. Okay, cool. So that gets accepted. Yeah, so that's pretty much it for this solution. Normal BFS, but with this modification to make it faster. Yeah, so that's pretty much it. Thanks for watching and see you on the next one. Bye.